All right, so here's another example in terms of counting. So ordered counting. So we have a rectangular table and it sits 10 people. It says that Grace will sit at the head of the table. And now if BJ can never sit beside Tommy or Jill, then in how many ways can the sitting arrangements be made? So this is a hard question to be able to do. Now there is, I guess, a way of interpreting this. I'll make one particular interpretation, okay, to give you some kind of a sense of how to approach this. Okay, so it says, so Grace will be sitting at the head of the table. So there's 10 people. So I'm going to, so here's a rectangular table, okay? Now, the head of the table, so Grace, you can just assume that, let's say maybe this is the head of the table. Although sometimes, people can say, well, I guess it could be either here or it can be here, right? So we're going to just assume that, head of the table is kind of at the top here. So that's the head of the table. Now, the rest of the question, so if BJ can never sit beside Tommy or Jill. So Grace is fixed. All right, so Grace is fixed at the head of the table. Now I can rearrange 9 people. All right, so there's now 9 remaining people that I would have. So I guess it would be kind of 1, 2, 3, 4, 1, 2, 3, 4, and I guess we can sit another one here. Okay, so that's 9 people that I can rearrange. So the total number that I can rearrange is 9 factorial, right? So there's 9 factorial ways of being able to rearrange this. That would have been easy if we didn't have this kind of constraint that BJ can never sit beside Tommy or Jill. So what I'm going to do now is I'm going to say, okay, so that's the total minus. Now, when is BJ, okay, sitting beside Tommy? Okay, so when are they sitting beside each other? Now, I can arrange them, right? It's either can be, BJ Tommy or Tommy BJ. Okay, so this is just 2 factorial ways of changing them around. And now that will leave me, okay, so I guess if I would fix that, so that would leave me 1, 2, 3, 4, 5, 6, 7 different ways that I can order the rest. Okay, so I have 1 unit, so that is my BJ and Tommy, and then I still have 1, 2, 3, 4, 5, 6, 7 around the table, right? Around the table, and now I can kind of swap them where BT is just 1 unit. So that means this is going to be, I guess, 8 factorial, right? So 1, 2, 3, 4, 5, 6, 7, 8. So I can rearrange these in 8 factorial ways when B and T are together, multiplied by, 2 factorial, or just 2, because I can rearrange BJ and Tommy, either BJ Tommy or Tommy BJ. So that is the total, okay, when BJ and Tommy are together. Now I don't want them together, so I'm going to be subtracting it. And now the other one, it says that BJ can never sit beside Jill either. So notice this or, so Tommy or Jill. So that's going to be the same thing. So I would do the same thing. So it's say subtracting. So now BJ and Jill, so when they're together, so that's identical to 2 factorial, right? And then we would have exactly this, except with BJ and Jill. So that would have been 8 factorial. So 8 factorial ways multiplied by 2 factorial that I can swap these two. Okay, so that is now subtracting that. But it now brings something into light. And if you do this, you have the right approach. But you have actually counted something twice. So notice that what could happen in this seating arrangement, okay, so if you would be putting these in, so let's say, I would do something like this, okay, let's say BJ was here, Okay, Tommy, let's say, was here, and then Jill was here. So we have clearly, so BJ and Tommy, so this, that is getting counted here, right, and subtracted. But BJ and Jill, so this right here, is also being counted right here and subtracted. So we've counted, or we subtracted them 2 times. So we've over subtracted. Okay, so we have to be careful there. So that means that, you know, we shouldn't subtract them 2 times. We should just subtract them once. So we should actually add at the end. So addition. So this is going to be adding when BJ is kind of in the middle, right? Fixed. And then you have Tommy and Jill on the sides, right? And it can be either, you know, Tommy, BJ, Jill, or Jill, BJ, Tommy, right? Because the you know, the Tommy and the Jill can swap together, and that is, you know, so 2 factorial ways to, you know, to swap them together. And now this acts as 1 unit, right? So if this acts now as 1 unit, so what we have is, we have this big unit, so that's that. And then what else? What does that leave me? Well, that leaves me, so in terms of the number of seats still, that's 1, you know, 2, 3, 4, 5, and 6. Okay, so that's 6 extra ones that I have. 1, 2, 3, 4, 5, 6. And now I'm going to be rearranging all of this, so I have 1 big unit, you know, 2, 3, 4, 5, 6, 7. So it's going to be 7 factorial ways of rearranging those. And then when these guys were together, so that would have been that. And we have to add it, because what we don't want happening is we don't want to be subtracting it 2 times. So this is a rather, you know, kind of lengthy example where you have 9 factorial ways minus, right? Now it's going to be BJ and Tommy, so this is going to be 2 factorial times 8 factorial minus BJ and Jill. But then we have to be careful and we have to add this right here. And that's actually the setup. And if I'm going to leave the calculation to you. You can plug in those numbers and find out what the answer is. But very often this is forgotten. Okay, this. And the reason, again, we're doing that because of the fact that we have actually subtracted it 2 times here, when BJ is kind of stuck in the middle between Jill and Tommy. So we have to be careful with that. Okay, so that's another really nice example for this organized counting.